So if G is a cyclic group with generator has order n, then G to the K is a proper subgroup only if K is a divisor. And I have a nice picture of the subgroup lattice for C12. Where I want to go next is back to Theorem 2 that we started and prove part 2. So let's get that on the board. That picture, by the way, is also in our book. So we have the following. Still, G is a cyclic group with these conditions, and we want to show the following. That G to the K is equal to G to the M, two different exponents, give the same answer if and only if K is congruent to M modulo N. So this will give you a little introduction to number theory also. So I want to prove both ways, right? It's an if and only if, so I'm going to start on this side and assume, and one way to note that you're proving the direction is just draw the direction. I'm going to assume that K is congruent to M mod N. That means they have the same remainder when divided by N, right? So this is equivalent to saying that K minus M is 0 mod N. Think about it, if they have the same remainder, let's just write that up as a little sidestep. If K is equal to Ln plus R and M is equal to Sn plus the same remainder, then what do I get when I divide, when I subtract them? The R's cancel out and I get a multiple of, so then little number theory proof, K minus N is equal to L minus S times N. So that's why it's a divisor when I subtract. If they're congruent modulo a certain time, means they have the same remainder. So we assume that we have that. That means that K minus M divides N, right? Or it's equal to something times N, right? Then, clearly G to the K minus M is equal to G to the Ln, but what's G to the Ln? Any multiple of N. N is still the order of that thing, so what's G to the Ln? 1, right? That's G to the N to the L equals 1 to the L. Is 1. Because N is the order of that element, the generator, right? But what does this mean? What is G to the K minus M? Well, that's G to the K times G to the minus M. Must be 1. So then if I multiply both sides, what do I want to multiply both sides by? Yeah, I can start here and say G to the M is equal to 1 times G to the M. What's 1 equal to? It's equal to that. And what's G to the minus M times G to the M? Those are inverses, right? So that's just the identity. So this is G to the K. So I proved that G to the M is G to the K, as I wanted to. Let's go the other way. So still the same assumptions. G is a generator of our group. The order of G is n. And I want to suppose that G to the k equals G to the m. Well, then clearly G to the k times G to the minus m is equal to G to the m times G to the minus m. Well, what's that equal to on the right side? 1. So G to the k minus m is equal to 1. But from our previous theorem, that can only be true if k minus m divides n, right? Because g to the something we proved, that's the first step, right? G to the something is 1 only if this is a divisor of n. Well, that means that k minus m is equal to something times n, which means that that's congruent to 0 mod n, which means that k is congruent. And we have our other direction. So this connection between number theory and cyclic groups is important. Okay. Let's just do a couple of other problems to fill out our day. Step 3 of this theorem, part 3 of this theorem, which is theorem 2, says that G is generated by the powers little g. And that proof is pretty easy. Okay, let's do some exercises. Again, to put the concrete behind the theoretical. See how we use this stuff. So let's start. This is section 2.4. So assume G is generated by G. And let's do this one. The order of G is 10. Find all the generators of G, all the other generators. So G must, by our previous work, what else will generate G? Will G squared generate all of G? No. Good. Will G cubed generate all of G? Yes. Why? Because 3 is not a divisor of 10, right? Good. What else will generate? G to the 4th? Yes. What else?
G to the 6th.
Yes. What else?
G to the 7th.
G to the 7th. 8th?
Mm-hmm.
Sure. Once I get past the halfway point, all the rest of them have to generate the group, right? Because they can't be divisors. About 10th. That's the idea. So that's it. This group has 6 different generators. And that's not unusual. Remember, we had this group. In the complex numbers, right? If I start with -1 and take all its powers, I only get 1 and -1, right? I never get I by starting with -1. But if I start with I get everything. I squared, I cubed, etc. It's the same thing, right? This actually is a cyclic group generated by I, but it's also generated by minus I. It has two generators. If you take the powers of minus I times minus I is still I squared, which is minus 1. So that's not too bad. That was exercise number 1.
So we just had to find
Find the generators.
Okay.
So they're all the ones that are all the powers that are divisors. And the other ones will generate subgroups. G squared will generate a subgroup. G 5 will generate a subgroup, and that's it. Those are the only two divisors. Let's do another one of these. 2.4.4. This was only part B, by the way. And we'll do 2.4.4 part A and B. We want to determine whether G is cyclic. So our group here is, that's the symbol for the multiplicative group. I'm doing multiplication mod 7. So what's in here? 0 hopefully is not in there, because 0 has no inverse. Multiplicative. 1, 2, 3, 4, 5, and 6 are in there. We looked at this kind of idea before, modular multiplication. For example, what's 4 times 5 in this group? 4 times 5 is 20, mod 7 is 6, right? So it's closed, it has identity. The identity is 1 because we're doing multiplication. We have to throw out 0. That's kind of what this star means, because 0 has no inverse. It couldn't be a group. Is it cyclic? How do you tell? Well, 1 won't generate it, right? Because 1 times 1 times 1 times 1 times 1 is 1. Try 2. Well, I get 2, 4, 6, 8 is 8 mod 7? 1. And then I get 2, and then something's wrong.
Yeah, you got 3.
Let's try this again. Multiplication. 2, 4, 2 times 4 is 8, which is
2.
7 is 1, yes. I don't like this. Obviously 1. 2, 4. That's 8, which is definitely 1 mod 7, right? Okay. So it is a subgroup, right? That's all I have in it. Okay, so it doesn't generate it, right? That's all I get is 2, 4, 1. Just convincing myself. So how about 3? Let's generate with 3. We have 3. 3 squared is 9, which is 2. And then 3 times 2 is 6. And then 3 times 6 is 18, which is 4. And 3 times 4 is 12, which is mod 7. What? 5, right? And then 3 times 5 is 15, which is 1. So that's the whole group.
So once you get to 1, you can stop.
Well, that's all the elements, right? But yes.
Oh, never mind.
1 doesn't generate, so that's not true in this case. So it's cyclic. 2 doesn't generate, so it has a subgroup. And that makes sense, because there's actually 6 elements in the group, and so I can have a subgroup of size 3. And I guarantee in this case that 5 will be a subgroup of size 2, because 5 times 5 is 15, which is 1. So that's a little subgroup of size 2. But 3 generates the group. So it is cyclic. And that's the time. Let me give you some homework, huh? And we'll call it a day.
You want me to stop?
Yeah. No, leave it running. This time I'll get the homework on the board. So study 2.4. In work, the exercises. Number 1. A and C. Number 2. A and just A. And number 3, just B. That's good. Okay, we'll pick up here on Friday. And I think according to the promise was this. On this material.